Okay, so today should be November 8th. Carbs continued. So we're going to finish chapter 12. So remember, this is chapter 12 in the new book and chapter 16 in the old book. Now, everything we saw about carbs or sugars, monosaccharides, last time was that we saw them in what's called the Fisher projection. Okay, this is the one where they kind of look like a fish. But monosaccharides can adopt what's called a cyclic structure. Okay, and a cyclic structure really is just, it means it's in the form of kind of a cycle or a circle. And then they can either be 5 or 6 membered rings. And the conversion occurs because of the ability of the aldehyde and the ketone. So think back to our functional groups of aldehyde and ketone can react with an alcohol, which is the other portion of our monosaccharide. Now, when that happens, they are going to form kind of a new bond and interconvert into a ring. Okay, so it's because our aldehydes can react with alcohols to form something new, and ketones and alcohols can react to form something new. So what this looks like, looking at this example right here, I have glucose. Okay, so think back to how we talked about numbering and naming. And the nice thing about this figure is that it's colored. So we can see the numbers all the way down 1 through 6. And so you can see here that the 1 carbon here, okay, is reacting all the way down with the alcohol on carbon 5. Okay. So what that means now is the carbon 6 is up at the top instead of the bottom, and it kind of bends around, looks like kind of closing the loop, if you will. And then in the end, we have 1, 2, 3, 4, 5, 6. Okay. Now the carbon here is a special carbon. It's called the anomeric carbon. And it's also sometimes referred to as C1. Okay, and the reason why the anomeric carbon is important is because of the OH position that we're going to see. Now, I'm not going to ask you to draw from Fisher to cyclic structures, but I would like for you to know that it's the reaction of carbon 1 with the alcohol on carbon 5. Okay? And then carbon 1 is still going to be important. It's our anomeric carbon. Before we used it to determine whether this was aldose or ketose, but now it's going to be what we use to determine something else referring to alpha or beta. Okay. So the nice thing is this structure right here, it's not the same figure, but it is roughly asking us the same thing. So it says the structure shown on the left side with the OH group on the first carbon projected downward is the alpha form. The structure on the right side with the OH on the first carbon pointing upward is the beta form. So looking back at this right here, this is alpha. It means that if we're looking at the anomeric carbon, carbon number 1, if the OH on that carbon is pointing down, we call that the alpha form. If the opposite is true, and on carbon 1, the OH is pointed upward, we say that that's the beta form. Okay? So you need to remember this convention, okay? Because you're going to have questions on sapling that's going to ask you to pick the alpha or the beta, and then you're going to more or less probably see a multiple choice question on your test about what dictates alpha and beta forms. Okay? And so because these are what we call two stereoisomers, meaning they're same as far as structurally connected, meaning carbon 1 to carbon 2 to carbon 3 and so on and so forth, but they're different in space. And the best example of stereoisomers is to look at your hands. If you look at your hands, they always have pinky, ring, middle, pointer, thumb, right? That part's not different. However, they're mirror images of each other. So they're connected the same, but they're orientated in space differently. Okay, and so that's what we mean by stereoisomers. And so because these are specific types of stereoisomers, we call them anomers. which makes sense if you think back to what we're talking about. The anomeric carbon is the one that is different, and therefore they are anomers of each other. Mirror images, but same in some ways and different in other ways. Okay, so that's really all I would like for you to know about the anomeric carbon. And so here are some definitions to reiterate what we just got done talking about. So the anomers are stereoisomers that differ in structure around what was the carbonyl carbon, so that's our C1, in the straight chain or Fischer projection form of the monosaccharide. Okay, so kind of reiterating what we said before. The anomeric carbon is the carbon atom that was on the carbonyl, C1, in the straight chain form of a monosaccharide. Now, mutarotation is a specific definition that relates to an ongoing interconversion, meaning it's flip-flopping back and forth between the anomeric forms of the monosaccharide to form equilibrium. So what that means is if we go back up here, alpha and beta, the OH group is flipping up and flipping down. And it's happening so fast that it's really hard to see it happening unless we take really quick images. So if you think about taking a movie, like a video on your phone, if you press play, the video shows really quickly all the motions happening. But if you did image by image, right, say someone made a funny face and you wanted to capture that funny face, you would go down to the individual image and you could take a still shot of how the face looked at that moment. And if we could do that for this type of process, we could catch alpha and beta individually, but when we look at it like the movie is playing, it's flip-flopping so fast back and forth that we really can't tell if it's alpha or beta at any given moment. Okay, so that's kind of what this is talking about, and it's referred to as mutarotation. All right, so that's all I really need you to know about the cyclic structures, both what it looks like, things to identify on it, definitions about it. And so we're going to talk about properties of monosaccharides before we move into di and polysaccharides, which will end out this chapter. So monosaccharides such as glucose and fructose are crystalline solids at room temperature, but they're super soluble in water. So off to the side here, what you can't see is think sugar. Hold on, Anderson. Go away. Think sugar. Okay, sugar we know readily dissolves in water. And this is true about glucose and fructose as well. Okay, solids at room temperatures. Now, the chemical behavior of the monosaccharides, just like we would imagine, is going to be determined by their functional groups. And this is something that we learned when we talked about functional groups, right? We defined functional groups based on the fact that they function differently, chemically speaking. Now, a reducing sugar is any carbohydrate capable of reducing a mild oxidizing reagent, so this is bringing back some redox memories, such as Tollens or Benedict's reagents, without first undergoing hydrolysis, meaning they stick around in solution and they don't undergo hydrolysis before they react. So, what does Benedict's test look like? The nice thing is the book is in color now so you can see. So what this says is Benedict's test was performed on 3 carbohydrates. We have fructose, glucose, and sucrose. Okay, and what the Benedict's test tells us is the solution containing sucrose remains blue because sucrose is a non-reducing sugar. So it's just a test we can do to test the chemical properties of monosaccharides. Okay, so that's all I need you to know about Benedict's reagent. All right, so disaccharides. Just as it sounds, monosaccharides, if we think about mono as one, saccharide meaning sugar, okay? And we want to break that now into something else. Di means two. We learned that back when we talked about covalent nomenclature. So now we're talking about two sugars. So what that looks like is maybe a little surprising, but disaccharides are going to be sugars composed of two monosaccharide units that are joined by what's going to be called a carbon-oxygen-carbon linkage that is better known as the glycosidic linkage. Okay, so it's going to look like a carbon-oxygen-carbon linkage. Now, it's going to continue on. This glycosidic linkage can produce more complex carbohydrates such as disaccharides or polysaccharides. So poly usually means many. Saccharides is still going to mean sugar. So now we're talking about many sugars. Okay, so what does that look like? That might be the more important question. So here is an image from your book, and it shows that we have an alpha, so alpha D-glucose with another alpha D-glucose coming together. And so the reaction is going to occur between the anomeric carbon and the OH group on carbon number 4. So now if we look at what happens from left to right, we have the formation of a carbon-oxygen-carbon bond. And it forms between C1, ooh, that's not a good color on that. Let's erase that. C1OC4. Okay, so that's the ones that it's forming between. Okay, and we're going to have two different types of options for the types of linkages that form. Okay, so we're going to have what's called an alpha or a beta glycosidic linkage. So the one that forms here is alpha maltose. So there are three of the most common disaccharides. The first is maltose, lactose, and sucrose. And sucrose is actually the sweet sugar that we're familiar with. Glucose we tend to think of as sugar. It is a sugar, but it's not sweet. It's actually really bitter. Sucrose is the one that we think of as being sweet and what we sweeten our foods with. So we're going to learn a little bit of information about these different sugars. So the first one that's on here is maltose. Maltose is formed by the hydrolysis, if we were to take maltose and break a water bond, so that's what hydrolysis means, it's H2O breaking with water, it's going to produce 2 D-glucose units, which is what we saw up here, okay? So what that means is that glucose plus glucose equals maltose, okay? And then the reverse must be true. If I take maltose and break it in half, I have a glucose and a glucose. So maltose is a reducing sugar, meaning that if we did Benedict's reagent, it would turn the solution brown. Okay, so think back to the blue. The blue that stayed was sucrose, and sucrose was non-reducing. So, as we saw before, the glucose units in the maltose are joined together through the alpha linkage of carbon 1 on the glucose and C4 on the other glucose. Okay, so it's defined by an alpha linkage. Okay, between the glucose and carbon 4. And this is a repeat of the slide. Hopefully I didn't miss one of the other ones. Okay, so now on to lactose. Most people know the word lactose because of lactose intolerant, and we're going to talk a little bit about that at the end. So lactose is a reducing sugar, and it's made up of 1 molecule of galactose and 1 molecule of glucose. Okay, so it's going to be galactose plus glucose equals lactose. And instead of having a alpha glycosidic bond, it's going to be defined by a beta glycosidic bond. And the question we're going to look at the differences between alpha and beta. Okay. So the two monosaccharides are obtained from lactose by acid hydrolysis or the catalytic action of the enzyme lactase. Okay, so this is kind of an important new thing that we didn't see in the last one. And so we know that sometimes adults and children suffer from the deficiency of lactase. And what that means is if you are deficient in lactase, it means that you usually end up being lactose intolerant. And so that's what this says right here. Lactose intolerant is the inability to digest lactose found in milk or dairy, so things that you eat or drink, due to the deficiency in the enzyme of lactase. Because what it means is it cannot break down this right here, okay? Because the enzyme lactase is absent, or it doesn't work very well. So you will take things like Lactaid, which will aid in all of that, or you avoid dairy altogether, maybe almond milk, soy, and so that's what it means to be lactose intolerant, and that's what the cause of it is. Now, galactosemia is a genetic disease caused by the absence of one or more of the enzymes needed to then convert the galactose to glucose. Okay, so we haven't quite talked about why this is important yet, but galactosemia is the fact that we can't take this galactose and then turn it into glucose, which is part of the digestive process of these disaccharides. Okay, so you need to know these two on a definition level and how they relate to these health deficiencies. Okay, so this was our second one. Try to make sure we don't get mixed up. All right, so sucrose. This is our sweet sugar. Okay, and so this says right here that sucrose is unique among the common disaccharides as it has an alpha beta glycosidic head-to-head linkage. Okay, so it's just unique in the way that it combines to form its disaccharide. Now, we saw earlier that sucrose was a non-reducing sugar, which meant that when we did Benedict's test, it was going to stay, hopefully you say blue, and that is true. It is going to stay blue. So we know that in Benedict's test, we're going to see blue. Now, I should have drawn or put a picture of the sucrose in here. But sucrose is a combination of 1 glucose plus 1 fructose to make sucrose. And I'm going to do my best to draw this structure correctly and neatly, more importantly. So what makes it unique is, remember how we talked about C1 coming together with C4, and that's not what happens here. Okay, so here's carbon 1, and then let me make that more straight. Just get the backbone down, that'll be easier. The nice thing is once I get this up, you can take a picture of it and that will help. Okay, so we have 1 and 2. Okay, so instead of the bond forming between 1 and what would have been 4, the alcohol in 4, that's not what happens here. The bond is going to form between 1 and 1. Okay. If you look at the image in the book, it's kind of confusing because the numbers don't quite line up with the carbons, but hopefully this will help. Okay, so that's what makes it unique. And so they call it an alpha 1. Oops, alpha. I need to make that. Alpha 1, beta 1. Okay. So if we take dilute acid or the enzyme sucrase, we would then break it apart into glucose and fructose, which we've already set up here, that these are the two monosaccharides that come together to form the disaccharide. So now you have the three most common disaccharides, what they're made up of, and some various information about their properties and their structures. All right, so now we are going to practice. So this is on page, goodness, where did my notes go? Should be on page 338, question 4. And just make sure at the top you're going to write that today is November 8th and this is your in-class assignment. And we're going to answer question 4A and 4B. So it says, for each disaccharide, indicate whether the glycosidic linkage is alpha or beta. Okay, so I'm going to zoom in. And so what we're looking for is we want to see, first we have to look at the anomeric carbon. And remember, the anomeric carbon is always going to be the carbon that is directly to the right of the oxygen. Okay, so I find the oxygen in the ring and the anomeric carbon is the next one to the right. So in this case, I'm looking at whether or not the oxygen points up or down. So in this case, in the first one, it's really clear to me that the oxygen is pointing up from anomeric carbon number 1. And we learned that when the OH group is pointing up, right, we said that up there that OH points up, that this is a beta anomer, which makes this a beta glycosidic linkage. Okay, so remember up here, we said that if it pointed up, it was beta, points down, it's alpha. Okay, so that's all we're doing. We're not looking for anything other than whether or not the oxygen on the anomer is pointing up or down. So if I look at the next one, I've already identified my anomeric carbon. I'm going to highlight the bond that I'm looking at, and then what do you guys think? I can't hear you say the answer, but it's obvious to me here that the bond is pointing down towards the floor and not up towards the ceiling like the last one was. So this means that the OH, it was pointing down, making that an alpha anomer, making this an alpha glycosidic linkage. Okay, so I hope it's clear to y'all that the beta has like this weird little tail sticking off of it, and the alpha looks like a little fish. Okay, sometimes when the pen gets a little bit thicker, it's hard to see the exact details. Okay, so that's all that it means earlier when it was saying that it's an alpha or a beta linkage, is the direction of that oxygen off of the anomeric carbon. Okay, so take a few minutes to get your stuff written down that you need, and then we're going to talk about polysaccharides. And just make sure you write your name on the top of the paper, and make sure to give it to Dr. Morris before you leave class. All right, so we said earlier that polysaccharides are many sugars, right? So we should expect that we're going to start talking about more monomers coming together, more glycosidic linkages forming, and that's exactly right. And so we call these, when they start to become very, very large, we start calling them polymers, which just really means many things that are being hooked together. So it is going to apply to your DNA, to proteins, to carbs. So polymers are something that we see a lot in biochemistry, which is where we are right now. And they are normally on the order of tens to thousands of monosaccharides that are all joined together by those glycosidic linkages. Okay. Most of them are non-reducing carbohydrates, so they are not sweet tasting, and they do not undergo mutarotation. Okay, so these are just kind of fun facts about polysaccharides, is that they are non-reducing carbohydrates. They are they are not sweet tasting, and they do not undergo mutarotation, which was the flip-flopping of the alpha beta that we talked about earlier. The three most common polysaccharides are starch, glycogen, and cellulose. Okay, and so we're not going to worry about there being referred to as this, because we're not going to see any of that. Okay. We won't worry about this one either. Okay, I just want you to know that the three most common ones are starch, glycogen, and cellulose. And we're going to spend just a little bit of time talking about each of them and give you some information more specific about each one and what makes them different. So starch is the first one. It is the most important source of carbohydrates in the human diet. So that sounds to me like good test material. And it accounts for more than 50% of our carbohydrate intake. So what is starch? It is a combination of two polymers, amylose and amylopectin. Okay, so amylose plus amylopectin. And I may say these like a real southerner. Equals starch. So amylose is a linear polymer of just glucose units, and amylopectin is a branched polymer of glucose. Okay, so what does that mean? That is a great question. So I'm going to show you an image of both so that you can see the difference between what I mean when I say linear and what I mean when I say branched. So here's amylose. Amylose is a straight chain of glucose, so you can see they're just one after another the whole way, all the way, and they repeat on and on and on and on and on to infinity in theory. And you can see here they have this kind of coil structure. Now, amylopectin, we said, was branched. And so this is what it means to be branched. You're going to have long chains, but then like a tree, it's going to have tree branches, right? If we think about a tree, it's going to have branches, and do not judge my tree. Okay, that's what this means, right? We call that branches, and structures can be branched just like that. So that's the main difference between amylopectin and amylose. Now the next polysaccharide is called glycogen. This is the energy reserve carbohydrate of animals. Sounds like another test question. It is structurally very similar to amylopectin, though glycogen is considered to be more highly branched instead of being long branches like we see up above. They are considered shorter. Okay, so very similar to amylopectin, except more heavily branched with shorter branches. Glycogen can be broken down into its glucose subunits by acid hydrolysis or by the same enzymes that catalyze the breakdown of starch. Okay, so similar in that sense. All right, cellulose. Cellulose is a fibrous carbohydrate found in all plants, and it's the structural component of plant cell walls. It's a linear polymer of glucose. It exhibits little interaction with water or any other solvent, so hence why it makes a great cell wall. It yields D-glucose after complete acid hydrolysis. And fun fact, humans are not able to metabolize cellulose as a source of glucose because the glucose units are linked by beta 1,4 linkages. So who eats cellulose? Cows, horses. Okay, they have the ability to break down the cellulose that we don't. So what does cellulose look like? Kind of like this, in black and white with fuzziness. Okay, so this should have taken, I've got my timer on, about 30 minutes. So what I would like for y'all to do now, if there's time, which hopefully there is to ask questions about Chapter 12 homework. Okay, this should be homework number I don't remember the exact homework number. Let me see. I've got it right here. Homework 16. If you have questions about it, go ahead and take the 20 minutes left in class to go through those. Dr. Morris should have a printout of the sapling homework with the answers filled in to help y'all. I hope all that is going well, and if you need anything, please email me, and I will get back to you as quickly as I can.